Hello students, today we will see the theory part 12 of chapter 8 Organic Chemistry, some basic principle and techniques, in which we will cover NCERT section 8.9. This is the disclaimer. Now, once you have attended the lecture, you will be able to understand the chemical reaction which are involved in the qualitative analysis of organic compound. So by qualitative analysis, we mean that we are only interested in the type of element which is present in the given organic compound. Okay. Now, if I talk about the specific sections of the NCERT, then the name would be for 8.9, it is qualitative analysis of organic compounds. Then in that, we will see the detection for carbon and hydrogen, which is NCERT section 8.9.1. After that, we'll see the NCERT section 8.9.2, which is for the detection of the remaining elements. Covering this theory part will help us to do some questions. So we'll do the in-text question 8.17. Now, let's start with the detection of carbon and hydrogen. If I just simply define qualitative analysis, then it is the process of identifying the type of element which is present in a given organic compound. We don't have to worry about their quantity. We have to only know that what are the species that are present in the given organic compound. If I talk about some key points about organic compounds, then the organic compound primarily contains carbon and hydrogen. So this is important because these two elements form the backbone of organic chemistry, creating a vast array of structures and functions. In addition to carbon and hydrogen, organic compound may also include elements like nitrogen, sulfur, halogen, and phosphorus. Now, qualitative analysis involves identifying these elements which are present in organic compound. Now, this step is very crucial because it helps us to understand the compound's potential behavior and interaction. It is like piecing together a puzzle to see the bigger picture. So here your bigger picture is organic compound and your pieces are atoms. So starting with the detection of carbon and hydrogen. Now, carbon and hydrogen are identified by hitting the given organic compound with the copper 2 oxide. So here 2 is representing the oxidation state of copper. Now, how we'll do it? As I said so you have to heat the given organic compound with COO. So it will give you 2 moles of copper and 1 moles of carbon dioxide. So again, I'm repeating it. So if you heat the organic compound with 2 moles of copper oxide, it will give you 2 moles of copper and 1 mole of carbon dioxide. Here, the copper 2 oxide is acting as an oxidizing agent and facilitating the given transformation. To confirm the presence of carbon dioxide, we will pass the gas through the lime water. So the gas that you are receiving after the reaction, we will pass it to the lime water, whose chemical formula is CaOH, calcium hydroxide, so CaH whole twice. The lime water will turn milky if there is the formation of calcium carbonate, a white precipitate. Now this visual change is a clear indicator of carbon dioxide and thus carbon in the organic compound. So this test is a classical method used in the qualitative analysis for carbon and hydrogen. Now moving on further. Next we have for the detection of hydrogen. So previously was for the carbon only. Here is your reaction. So if you heat your organic compound with COO, then what you will get? You will get copper and water. Now this reaction is important because it shows us how hydrogen is formed into water, transformed into water, which we can then detect. Remember, the presence of water is our clue that the hydrogen was present in the original compound. Then to confirm the presence of water, we use a simple test. So water vapor is passed over anhydrous copper sulfate, which is initially white. When it turns blue, it indicates the formation of hydrated copper sulfate, confirming the presence of water. This color change is a clear visual cue that your hydrogen was present in the organic compound. Now, after completing the detection of carbon and hydrogen, let us study about the Leysinck's test, which is useful for other elements. Now, this test is used to detect nitrogen, sulfur, halogens, and phosphorus in the given organic compound. In this test, the elements that are covalently bonded in the compound are converted into their ionic forms. So this is achieved by fusing the compound with sodium metal. Upon fusion, it leads to some key chemical reactions. So let us look at the sodium fusion reaction. So if your detection is for nitrogen, then the reaction involves sodium, carbon, and nitrogen forming sodium cyanide. So this reaction is important because sodium cyanide is a detectable compound that indicates the presence of nitrogen. Then for sulfur, the reaction involves sodium, sulfur, which forms sodium sulfide. So this reaction is significant because sodium sulfide is also a clear indicator of sulfur in the given compound. Now, if halogen is present in the organic compound, then the reaction will involve sodium and halogen forming sodium halide. So the halogen can be chlorine, bromine, or iodine. This reaction is useful because sodium halide are easily identifiable, confirming the presence of halogens. Now moving on further. Now, how do we prepare this sodium fusion extract? So this method is clearly teached in every classroom in the practical classes. Now, once you have done this, you can use this product after the fusion cyanide, after the fusion process, and the sodium forms compounds like cyanide, sulfide, and halide. Now, the sodium salt formed during the reaction, such as NaCN, Na2S, NaX, are extracted by boiling the fused mass with distilled water. So this step is essential for isolating the compound in a solution that we can test further. The solution we get from this process is called the sodium fusion extract. It is important because it contains the ionic compound we need to test for the presence of elements like nitrogen, sulfur, and halogen. Finally, we subject the sodium fusion extract to further tests to confirm the presence of specific element. Now, moving on further. So let us begin with the test of nitrogen. How do we do it? So the first step involves the preparing of sodium fusion extract. So this extract is boiled with iron 2 sulfate. So obviously you will first prepare the sodium fusion extract. Once you do this, you can take this extract and boil it with the iron 2 sulfate. Here again, the iron is in the second oxidation state. And then you will acidify it with the concentrated sulfuric acid. Now, what will happen? The sodium cyanide reacts with iron 2 sulfate to form sodium hexacyanidopyrrate with a oxidation state of 2 for the iron. You can see here it in the chemical equation as well. Now, upon heating, some iron 2 ion are oxidized to iron 3, and this iron 3 ions react with sodium hexacyanidopyrrate after the completion of reaction. Now, formation of Persian blue, which is ferricyanide, is a distinctive blue color. This color change is a visual confirmation of the presence of nitrogen in the compound, and it is a classical example of how a chemical reaction can be used to detect specific elements. The hexacyanidopyrrate 2 is Persian blue in color. To summarize, the preparation of Persian blue confirms the presence of nitrogen in the compound. Now we are going to study this test, which is a method used to detect other elements like sulfur in organic compound. To do this, what we will do? We treat the sodium fusion extract with acetic acid and lead acetate. So it is added to it, and if black precipitate of lead sulfide form, then it indicates that the sulfur is present in the given sodium fusion extract. Moving on to the second method for detecting sulfur. So here we treat sodium fusion extract with sodium nitroprusside. So if a violet color appears, it confirms the presence of sulfur. Now this color change is due to the formation of complex ion, which is a common way to detect specific ion in a solution. Now moving on further, what key points can you remember for this given test? In case of nitrogen and sulfur, both are present in an organic compound. sodium thiocyanate is formed and it gives blood red color. So here you can see we have Na, then we have carbon, then we have nitrogen and sulfur. Now this NaSCN is formed and this SCN minus further reacts with the iron 3 plus to form the blood red complex, which is FeSCN with a charge of 2 plus. This color change is a clear indicator for the presence of both nitrogen and sulfur in the compound. Now we are going to study this test for halogens. First, let's focus on the detection of halogens. So halogens are elements like chlorine, bromine and iodine, which are often found in organic compounds. Identifying them is important for understanding the compound's properties and potential reactions. To detect halogen, we use a sodium fusion extract. This extract is acidified with nitric acid and then treated with silver nitrate. The reaction forms a precipitate which helps us to identify the specific halogen present. The equation for this reaction is a halogen ion, I will say a halide ion reacting with Ag plus to give us a salt of silver. Now the salt can be of chlorine, bromine and iodine, or three of them. Okay. White precipitate is formed. So whenever a white precipitate is formed, it indicates that the halogen is nothing but a chlorine. So this precipitate is soluble in ammonium hydroxide, which is a key characteristics of chlorine detection. After that, if you don't observe a white color and you observe a yellow precipitate, then is a sparingly soluble in ammonium hydroxide, then it suggests that your halogen is bromine. Further, if the yellow precipitate that is insoluble in sodium hydroxide points to the presence of iodine. So basically, if the yellow precipitate is soluble in ammonium hydroxide, the halogen is bromine. If it is not soluble in ammonium hydroxide, then the halogen is iodine. What are the key points you should remember? If nitrogen or sulfur is present in the compound, they can interfere with this halogen detection. Now to prevent this, the sodium fusion extract is boiled with concentrated nitric acid to decompose any cyanide or sulfide. Now these ions, if not decomposed, it would interfere with the silver nitrate test for halogens, and it is important to eliminate this possibility to ensure accurate detection by eliminating this potential interference. Now we will study this test for phosphorus. For phosphorus, we heat the compound with an oxidizing agent such as sodium peroxide. So the role of oxidizing agent is to facilitate the conversion of phosphorus into a detectable form. Once the compound is heated, any phosphorus present in oxidized to form phosphate. Okay, so it oxidizes to form phosphate. This transformation is essential because phosphate is a form that can be easily identified in given subsequent steps. Next, we will boil the solution with nitric acid and treat it with the ammonium molybdate. So this step is crucial as it prepares the phosphate for the final detection. The chemical reaction here involves the conversion of sodium phosphate to phosphoric acid, then to a complex with ammonium molybdate. The appearance of the yellow color, I would say, or the precipitate indicates the presence of phosphorus. Next, we have some questions here. You have to write the resonating structure for the given compound, which is CH2, double bond CH, single bond CHO. And you have to indicate the relative stability of the contributing structure. How will do this? So first, look at this structure of the given compound. So this molecule consists of a carbon-carbon double bond and an aldehyde group. Now recognizing this functional group is important as they influence the molecule's behavior. Here is a visual representation of that same structure. Notice the arrangements of the atoms and the double bond. This structure is the starting point for understanding its resonance forms. Now let us discuss the concept of pi bond. So in pi bond resonance, the resonance occurs between the pi bond which can delocalize electrons across the structure. So this delocalization is key to understand the molecule stability. So here is a visual representation of how the pi bond resonance is occurring in the given molecule. Now, let us look at the first resonating structure. Notice how the double bonds are arranged. This structure will serve as our reference point for comparing stability. Notice how two different flow of electrons, red and green, can generate two different resonating structure 2 and 3. Now let us discuss rule number 1. So now we are going through these rules to compare their stability. Rule number 1 focuses on the number of pi bonds. So pi bonds are crucial because they contribute to the stability of a compound, and more number of pi bonds generally indicates that your given compound or the given resonating structure is very stable. Remember that the structures with more pi bonds are typically more stable. This is because pi bonds provides an additional electron delocalization which stabilizes the molecule. Now let us compare the resonating structure based on their pi bond. So this comparison will help us to determine which structure is the most stable. In structure number 1, we have 2 pi bonds. So this is our key point because having more pi bond often leads to greater stability. Structure number 2, on the other hand, has only 1 pi bond. So this reduction in pi bond typically results in less stability compared to the structure number 1. Similarly, the structure number 3 also has 1 pi bond. So this would be like your structure number 2. So it is again less stable than the structure number 1 due to fewer number of pi bonds. In conclusion, we can say that structure number 1 is the most stable one because we are following this given rules in a canonical manner, and the rule number 1 clearly indicates that the structure number 1 has a greater number of pi bonds, so it will be the most stable due to better electron delocalization. Now, next, if we talk about the remaining 2 resonating structure, so it would be 2 and 3. For this, we have to look upon the rule number 2 because the number of bonds is same. The rule number 2 is about the octet rule. So this rule states that if all the atoms in the given compound have their complete octet, then it would be the most stable one. Structures that satisfy the octet rule are generally more stable. Now we see that structures satisfying the octet rule are more stable. So this is because having a complete octet allows atoms to achieve a noble gas configuration which is energetically favorable. Keep this rule in mind as we compare different resonating structure. Let's compare the resonating structure 2 has an incomplete octet for carbon, which makes it less stable. So structure number 2 has an incomplete octet for oxygen. Then structure number 3, again we have an incomplete octet for oxygen. So structure number 2 and 3 both cannot satisfy this octet rule. Therefore, they are equally unstable according to the rule number 2. Now moving on further. Next, what we have? We have our rule number 3. So rule number 3 is based upon charge. It tells us that the neutral structures are generally more stable than the charged ones because charged structure often have higher energy and less favorable. If we look at both of the resulting structure, then they both are charged, which makes them less stable according to the charge rule. So again, their stability could not be decided with this rule number 3. Now moving on to the next rule, what we have? We have the rule number 4. What we are comparing 2 and 3 because 1 is already the most stable one. So rule number 4 is about the placement of the charge. Remember, the negative charges are more stable when they are on electronegative atoms. This is because electronegative atom stabilizes the extra electron, whereas the positive charges are more stable on the electropositive atom. Let us compare the resonating structure. So we will evaluate them on the basis of the charge and the overall stability they provide to the molecule. In the structure number 2, we see that the negative charge is on a more electronegative atom and the positive charge is on a more electropositive atom. So you can look at it in structure number 2. Oxygen is carrying the negative charge and carbon is carrying the positive charge. Now this arrangement is favorable and contributes to the stability of molecule. Whereas in the structure number 3, the oxygen is carrying a positive charge while the carbon is carrying a negative charge. Now this would be less favorable because oxygen is more electronegative and prefer to hold a negative charge rather than a positive charge. Now based on our analysis, we can conclude that structure number 2 is more stable than the structure number 3, and this conclusion is drawn from the charge placement and electronegativity of the atoms involved. If I talk about the overall stability of the resonating structure, then they can be ranked as follows. So structure number 1 is the most stable one due to the greater number of pi bonds. Then we have structure number 2 due to the proper placement of the charge. And then we have the structure number 3. So this was all from the theory part, and the question part is also covered. Now we will summarize our today's lecture. So we started with the detection of carbon. To do that, what we do, we heat it with the oxide of copper. In that process, the carbon is oxidized to the carbon dioxide. Now to detect this, we pass this carbon dioxide through the lime water, which is calcium hydroxide, CaOH whole twice. If carbon is present in the given organic compound, so of course it will contain, if in the given compound I would say, then it will turn your calcium hydroxide solution milky. Now let us move on to the detection of hydrogen. So what is the reaction? So hydrogen is oxidized to H2O, and the H2 vapors are tested by passing it through the anhydrous copper sulfate, and upon exposure to the moisture, your anhydrous copper sulfate is hydrated to form a blue color. Next, we have this Lessing text, which is used for the detection of nitrogen, sulfur, halogen, and phosphorus in a given organic compound. If I talk about the nitrogen's detection, so here we boil the sodium fusion extract along with the iron 2 sulfate, and then we acidify it with the concentrated sulfuric acid. In that process, your hexacyanide of ferrite, which is Persian blue in color, is formed, and it is a clear indicator that a compound is containing nitrogen. Then we have formation of Persian blue color. So this is confirming that the nitrogen is present in your given organic compound. Moving on to the next, we have detection for sulfur. So for sulfur detection, we have two methods. So method number 1 involves the formation of black precipitate of lead sulfide, which indicates the presence of sulfur. This method relies on the reaction between sulfur and lead, resulting in a visible black precipitate. Then, if I talk about the method number 2, it involves treating the sodium fusion extract with sodium nitroprusside. The appearance of a violet color further indicates the presence of sulfur, and this method provides an additional confirmation, ensuring the accuracy of our detection process. Next, we talked about the detection of halogen according to the test. Starting with chlorine detection. So whenever we see a white precipitate which is dissolved in ammonium hydroxide, then the given halogen is halide. Okay, so that is chlorine, not halide, chlorine. Then if you get a yellow precipitate and the yellow precipitate is soluble in ammonium hydroxide, you would say that there is the presence of bromine. Okay, the halogen is bromine. Remember, the given salt is only partially, or I would say sparingly soluble, not completely soluble. Then we have the yellow precipitate, but in this time it is completely insoluble in ammonium hydroxide. In that case, it will confirm that we have iodine present in the given organic compound. Talking about the detection of phosphorus. So the compound is first heated with an oxidizing agent. Suppose we have this sodium peroxide. So this step is crucial because it converts the phosphorus into detectable form. Then the phosphorus present in the compound is oxidized to the phosphate. And finally, the appearance of a yellow coloration of or precipitate indicate the presence of phosphorus. So this was all for today's lecture. Thank you for joining the session. I hope you enjoyed it.